Cosmology has changed forever with the launch of James Webb on Christmas Day 2021. Ever since it opened its impressively sharp, high-resolution infrared eyes, James Webb looked back at some of the earliest stages of the universe, gathered sharp, pristine, and beautiful insights of early star and galaxy formation, and provided insights into the formation of planetary systems, including our own solar system. But in some sense, James Webb was almost too good, far exceeding all hopes and expectations. Astronomers expected to find some of these infant galaxies with Webb, but they didn't expect to find so many. Webb's unprecedentedly deep views revealed a colossal surprise: a bunch of the impossible early galaxies. Even at these earliest times, these galaxies were too big, bright, and numerous to explain, some of which are even older than the universe. Our best cosmic predictions, based on lambda-cold dark matter, the standard model of cosmology, didn't expect what James Webb saw. In other words, discoveries made by James Webb could shake their understanding of galactic history. So, is the Big Bang and all of modern cosmology in trouble? Join us as we dig deep into how James Webb just found massive structures that could defy our current theories of the universe. The farther and farther back into the distant universe we look, we have a picture of what we expect to see. At some point, we should find the first and earliest bright, large, luminous galaxy, and we should see their number density rapidly decrease as we approach that limit. Before that, we should find only smaller and less evolved galaxies, decreasing in number and number density until we find the very first among those. Before that, we should only see individual star clusters and proto-galaxies, and these should be extremely blue and primitive, and again should only exist in low number densities the farther back we go. And finally, there should truly be a time where the very first stars and star clusters of all appear, and beyond that, there should be no luminous sources at all to observe, excepting the Big Bang's leftover glow itself. When we look into these deep depths of the universe and examine these galaxies, we're basically asking the universe, how did you grow up and come to be the way you are today? Given that we have a model of the universe, a mix of dark matter, normal matter, dark energy, and a little bit of radiation, we can arrive at predictions for what we expect to see in the universe at any given time. Looking at these distant objects with the James Webb Space Telescope, and with its spectroscopic capabilities in particular, allows us to test that model, and to see if we truly understand the universe we inhabit, or if, and how, we have to revise our picture of the cosmos. The James Webb Space Telescope is changing astronomy in many ways, from peering into the atmosphere of exoplanets to capturing stunning images of distant cosmic phenomena. But perhaps its greatest scientific contribution is its ability to observe galaxies that are so distant that looking at them is like looking back in time. Projects like Webb's SEERS, or Cosmic Evolution Early Release Science Survey, are scanning the sky to pick out some of the oldest galaxies we've ever seen. When scientists first turned Webb toward apparently empty patches of sky to look for these distant galaxies, they found something very strange. They didn't just find a few very old galaxies, dating back as much to just a few 100 million years after the Big Bang. They found far more of these galaxies than anyone had predicted. According to Michaela Bagley of the University of Texas, one of the leading SEERS researchers, the theoretical models didn't predict that these should be there. We still don't yet know how you can see a galaxy that bright, that early. One particular galaxy jumped out of the SEERS data straight away. Maisie's galaxy, named after the daughter of Stephen Finkelstein, one of the researchers, is 13 billion years old, making it one of the oldest galaxies ever observed. And it is much brighter and much bluer than anyone predicted. As Bagley said, when we found Maisie's galaxy, the surprising part was how is it in the universe? It's exciting that this is the universe we live in. It's a universe with a ton more galaxies than we thought. Webb is able to detect extremely distant galaxies because its instruments operate in the infrared wavelength. A small handful of extremely distant galaxies had been detected previously by the Hubble Space Telescope, which operates primarily in the optical light wavelength, which is equivalent to what human eyes can see. But as galaxies move further and further away from us due to the expansion of the universe, their light is shifted toward the red end of the spectrum in a process called redshift. The extremely distant galaxies that early universe researchers are interested in have light that is redshifted so far that it is no longer visible in the optical and can only be seen in the infrared. So Hubble's instruments were pushed to the limits to detect even a few of these galaxies, while Webb was able to detect many of them incredibly quickly, within a few days of the telescope beginning its science operations. When discussing these galaxies, scientists typically talk about them in terms of their age rather than their distance. You'll see researchers describe a galaxy as being from the first few 100 million years after the Big Bang rather than being located billions of miles from Earth. That's also because of the expansion of the universe, which creates a moving frame of reference that makes it hard to describe distance meaningfully. Examples include galaxies like Maisie's galaxy, which is described as being 13 billion years old. The light has traveled 13 billion years to get to us. But if we could see Maisie's galaxy today, it is much, much further away because in that time, the universe has kept expanding and accelerated its expansion. The time the light has spent traveling to us gives us more concrete information about when in the universe we're observing these galaxies. Initial estimations of the redshift, and thus age, of Maisie's galaxy were based on photometry, which works by analyzing brightness in images while using a small number of wide-frequency filters. These calculations suggested the galaxy had a redshift of 11.8, but Finkelstein and the Sears team wanted a more accurate age estimation. To do this, they made follow-up observations with James Webb's Near-Infrared Spectrograph, or NIR-SPEC for short. This allowed Finkelstein and colleagues to look at spectral lines created in light data, dictated by the absorptions and emissions of chemical elements at specific wavelengths. From there, they could pinpoint the actual redshift of Maisie's galaxy. It appeared to be 11.4. This means Maisie's galaxy is technically seen more recently in the universe than initially estimated, by a factor of tens of millions of years. Nonetheless, it is still considered immensely old. The James Webb captured the galaxy as it was just 390 million years after the Big Bang. This impressive age places Maisie's galaxy among the 4 oldest galaxies in the universe that have had their ages confirmed by spectroscopy, a technique that splits light into its component frequencies to better reveal its brightness, heat, and chemical composition. While such galaxies don't yet pose problems for leading models of cosmology, they suggest galactic formation began earlier and proceeded faster than expected in the universe, which theorists had previously predicted began churning out galaxies at the ripe age of 1 billion years after the Big Bang. As Fabio Pacucci of the Harvard-Smithsonian Center for Astrophysics said, "We're seeing a rise of massive galaxies faster than we thought previously." The ages of some of these early galaxies are estimated at just tens of millions of years. This could have implications for large structures of dark matter known as halos that sculpted early galaxies, and for the nature of dark matter particles themselves. One of the big open questions is, what is dark matter, says Sandro Ticella of the University of Cambridge. The first generation of galaxies is a sensitive probe for different dark matter models. On the other hand, we should be cautioned that some problematic and potentially model-busting early universe candidate galaxies still remain. Scientists had already produced models of what early galaxies would be like, and Webb contradicted them almost immediately. As soon as James Webb began looking for early galaxies, it found far more of them than anyone had predicted, and found that they were much brighter too. Light is a double-edged sword in the context of these galaxies. It's what lets us study the galaxies. But there's so much more of it than astronomers would have expected. The brightness of a galaxy can be related to its mass, because a galaxy's light comes from stars. If you assume a certain average brightness and mass of a star, you can roughly estimate the mass of a galaxy. But much of the modeling astronomers have done up to this point has led them to believe that there wasn't enough time for galaxies to get this massive in so little time. According to Jorge Moreno, an associate professor of astronomy at Pomona College, it's like if you went to a kindergarten and you saw a teenager. What's more, today, most galaxies are separated into two types: spirals, which are disk-like with arms of dust and gas, and ellipticals, which are more like spheres of smooth light. Until now, scientists thought that any galaxies from this relatively early period in the history of the universe would have been too young to have been forced into that binary yet. Instead, astronomers thought the galaxies would be blobs. But under James Webb's views, some of the early galaxies look a lot like galaxies in the local universe. They seem to have added structure and maybe even spiral arms. That wasn't something we really expected. The high level of structure and brightness in these galaxies is leading some astrophysicists to question the age of the universe. In an attempt to explain the impossible massive galaxies existing so early in the timeline of the universe, a researcher has posited that the universe is roughly twice as old as previously believed. They pushed the age of the universe from a spry 13.8 billion years old to roughly 26.7 billion years old. That's an interesting scenario, but it doesn't correspond to the evidences at hand. So, up to now, there's currently no consensus on what is the root of the discrepancy between the models we have and the data we observe with Webb. The answer could be related to dark matter and its role in the early universe, or it could be that the way early galaxies were formed was spurred on by forces that haven't been considered yet. However, it's worth noting that even before the James Webb Space Telescope, scientists knew that the early universe was a very different place from the universe today. Its galaxies were made almost entirely of hydrogen and helium, were shaped by tendrils of dark matter, and hosted enormous bright stars that lived fast and died young. While the laws of physics haven't changed over the past billions of years, the scale of the universe has, and that affects how those physical laws apply to galaxies. When the universe was smaller and denser, that affected the ways in which stars form in complex ways. As Bagley explained, if the universe is smaller, the density inside galaxies and outside galaxies is probably higher. If it's dense and hot, the gas won't collapse to form stars. If it's dense and cold, then you could get a ton more stars. Another way in which the early universe was fundamentally different is in its overall chemical composition. Heavy elements like metals were almost entirely absent in the early universe, because these elements were primarily formed within stars and spread by their explosive deaths, called supernovae. It took several generations of stars to spread these heavier elements through the universe and to be absorbed into stars similar to those we see today. The hypothetical earliest stars in existence are referred to as population 3 stars. Today's young stars are population 1 stars, and the numbering counts backward in age. They were much bigger, heavier, and bluer than stars today, and they gave off more ionizing radiation. Those differences are because of the way stars generate heat and light in a process called fusion. If a star is made only of hydrogen and helium, to do fusion, the star has to be hotter and denser than a star that has carbon, nitrogen, oxygen, Bagley explained. There's a different chemical pathway to create fusion, and that requires a larger size and more mass to support it. No one has ever observed a population 3 star before, and finding one is one of the holy grails of modern astronomy. but scientists believe it could be possible to find one using Webb. Anyway, James Webb was built primarily to transform our understanding of the early universe, and telltale evidence gathered by the James Webb Space Telescope suggests we're closer than ever before to finding elusive first stars of the universe. All of this discussion of billion-year-old history might seem rather abstract, but in fact, it's directly relevant to understanding the universe as we see it today, and as the James Webb Space Telescope is revealing in greater detail than ever before. That's because astronomy operates on such long time scales that we can't watch objects like galaxies across their lifespans. Most galaxies we see around us today look like the Milky Way, but we can't see them develop over time. To study that development, we need to look for distant and ancient galaxies, which Bagley refers to as baby pictures of the Milky Way. This is all about understanding how our Milky Way formed. It sounds cliché, but before we can understand where we are and where we're going, we need to understand where we came from. In addition, on the hunt for alien civilization, NASA has just revealed that 17 discovered exoplanets could house subsurface oceans buried below thick sheets of ice. These worlds, much like the icy moons of Jupiter, could therefore be promising places to search for biosignatures, chemical signs of life. While the exact composition of these worlds remains unclear, estimates of their surface temperatures from previous studies point them being significantly colder than Earth. They're also each less dense than Earth, despite being roughly the same size as our planet. As Lynn Quick of NASA's Goddard Space Flight Center said in a statement, "Our analyses predict that these 17 worlds may have ice-covered surfaces but receive enough internal heating from the decay of radioactive elements and tidal forces from their host stars to maintain internal oceans." In other words, while their host stars may not provide conditions warm enough to keep water in liquid form on their surfaces, these planets may exhibit processes that can generate heat below their surface. The stretching and compression of rock inside a planet as it gravitationally interacts with its sun, for instance, could provide significant amounts of internal heat, enough to sustain a subsurface ocean. The radioactive decay of heavy elements inside the core of a planet can provide intrinsic heat as well. Thanks to the amount of internal heating they experience, all planets in our study could also exhibit cryovolcanic eruptions in the form of geyser-like plumes. Quick said, cryovolcanism meaning, in short, ice volcanoes. The study drew on what we know from the geyser activity of two of Jupiter's moons, Europa and Enceladus. Two of the exoplanets named in the research, Proxima Centauri b and LHS 1140b, were particularly promising candidates for having oceans relatively near the surface. Since our models predict that oceans could be found relatively close to the surfaces of Proxima Centauri b and LHS 1140b, and their rate of geyser activity could exceed Europa's by hundreds to thousands of times, telescopes are most likely to detect geological activity on these planets, said Quick. Follow-up observations of these worlds will likely include astronomers capturing the emission spectra of light traveling through these planets' atmospheres. Chemicals and molecules erupted into the atmosphere from cryovolcanic activity may hold clues as to whether life might exist in the cold, dark depths of these worlds. In a one-of-a-kind event, scientists just announced that Mars's atmosphere, once as thick as if not thicker than Earth's today, is leaking into space. About 0.11 cube of Mars' atmosphere is pushed away every second by the incessant solar wind, the speedy stream of charged particles routinely blasted from the sun, which pervade the solar system and even reach beyond Pluto. But for a rare 2 days last December, some of that wind went away. Its sudden and dramatic disappearance caused the atmosphere on Mars's sun-facing side to swell by nearly 4 times its usual size, from its usual 800 kilometers to over 3,000 kilometers. The peculiar event was recorded by a NASA orbiter named MAVEN, short for Mars Atmosphere and Volatile Evolution, which has been observing both Mars's atmosphere and its response to the Sun's behavior since 2014. MAVEN's data showed other aspects of the Martian system, including the teardrop-shaped magnetosphere, the bow shock, and the ionosphere, expanded similarly. As Jasper Halikas, a professor of physics and astronomy at the University of Iowa and a member of the MAVEN team, said, "We're really off the charts here. This is something that we haven't seen at Mars before with MAVEN." The atypical episode, the first in nearly a decade of MAVEN's career, occurred after a fast-moving region of a solar wind overtook its slower counterpart and swept up the latter's material, leaving behind a sparse region. The emptied storm reached Mars on D-Sector 25, 2022, giving scientists a thrilling front-row seat to watch the planet's atmosphere balloon out, the way it might have been if it were circling a less windy star. According to Halikas, who is leading a new study, this was a Christmas present for us. Nature set up this perfect science experiment. With MAVEN's data of the unexpected dynamics on Mars, Halikas and his colleagues studied how extreme solar events and their absence influence the planet's atmosphere, an insight valuable to understanding its evolution. The findings also have implications for our understanding of Earth-like planets outside our solar system and how they interact with their host stars, the team shared on Monday. We could look under the hood at what physics is going on, how the dynamics are working, and really get a sense of those details, said MAVEN team member Skylar Shaver of the Laboratory for Atmospheric and Space Physics in Boulder. 2 days after the almost vacant storm passed Mars, the atmosphere around the red planet settled down to its original state once again, but not before bouncing a little like a jiggling plate of jello. A similar storm struck Earth in 1999, when our planet's atmosphere grew to 5 times its normal size. But there aren't often orbiting spacecraft positioned as well as MAVEN is now to study such events, the new atlas reported. Shannon Curry, the principal investigator for the MAVEN mission, suspects events like this were common during Mars' early evolution 3 to 4 billion years ago, when our sun was more fiery than it is now and perhaps blasted out storms once a week or even every day. Such extreme events were likely responsible for parching the red planet, a world scientists presume once hosted liquid water and offered conditions friendly toward life. Launched on Christmas Day 2021, the Webb telescope is the bigger, cooler sibling of the Hubble Space Telescope, equipped with super-powerful infrared instruments that make it a perfect time machine.
Well, it turns out it's so powerful it might have just shattered our understanding of the universe.
By peering into the past, James Webb allows us to detect incredibly old and faint objects, such as distant galaxies and celestial bodies from the early universe. However, the images captured by James Webb are causing quite a stir among astronomers and cosmologists, as they challenge the very foundation of our understanding of the universe. Thus, in the 2 years since James Webb launched, renowned American physicist Michio Kaku and other scientists have learned one thing: the early universe is a lot weirder than we thought.
That shouldn't happen. There should not be primordial galaxies that are bigger than the Milky Way galaxy that are only 500 million years old. Something is wrong. We may have to revise our theory of the creation of the universe.
Join us as we dig deep into how James Webb just proved us wrong. When Einstein first put forth his new theory of relativity, it forever changed how we think of space and time. Space isn't fixed like a 3-dimensional grid with universally agreed upon distances between any 2 points. Nor is time a continuously flowing entity where you can sync up your clocks, move anywhere you like, and be confident that your clock reads the same as anyone else's. Instead, we experience space and time as relative. Your motion through space affects your motion through time, and vice versa. This was the core idea behind special relativity, which led us to discard our older ideas of absolute space and absolute time, instead replacing them with the notion of space-time. As you move through space relative to another observer, your clocks appear to run differently according to Einstein's laws. Special relativity works perfectly for all observers, whether they're at rest or in motion, and represented an enormous leap in understanding our universe over Newton's original laws of motion. But this idea, brilliant though it was, didn't include gravity. The old Newtonian picture of gravity was inherently tied to absolute notions of distances and times and was incompatible with the notion of space-time. It took over a decade for Einstein to bring gravity into the fold, taking us from special relativity to general relativity, incorporating matter and energy into the equation. Instead of the flat space-time of special relativity, the presence of matter and energy allowed for space and time to be dynamic entities. No longer bound to be static, the universe could expand or contract depending on what was in it. Matter and energy told space-time how to curve, and that curved space-time dictated how matter and energy would move. This relationship, first put forth more than 100 years ago, has been tested by an enormous suite of experiments and observations, with Einstein's theory passing each and every one. General relativity applies not only to the gravity we find on Earth and elsewhere in the solar system, but on vast cosmic scales that dwarf our own. Galaxies, clusters of galaxies, and even to the entire universe itself. This last part is particularly fascinating. If we take a universe that's uniformly filled with matter and energy, including a combination of different forms of matter and energy, that universe must either expand or contract. It cannot remain in a static state for more than an instant, even if it starts off in one. In 1922, Alexander Friedmann demonstrated this, deriving from Einstein's theory, the Friedmann equations, the equations that govern the expansion of the universe. The very next year, Edwin Hubble measured the distance to Andromeda, determining that this spiral nebula was in fact its own galaxy far beyond and outside the Milky Way. Subsequently, we measured distances to large numbers of galaxies, while also independently obtaining measurements of the light coming from them. What we found, almost universally, was the following. First, the farther away a galaxy was, the redder its light was. Second, that this was true even though the stars inside the more distant galaxies were, on average, intrinsically bluer than the stars we seen in nearby galaxies. Third, the explanation for this was consistent with the idea that light emitted by galaxies with the same frequencies and wavelengths that light is emitted by here in our own galaxy was being redshifted by the expansion of the universe. Alternative explanations, such as tired light, disagreed with the observations, leaving only those explanations that included the expanding universe as viable. When taken all together, there was no escaping that conclusion. The universe itself was expanding, and that expansion was responsible for the observed redshift of light that originated from far away. To be fair, the expanding universe theory has the advantage of internal consistency. A theory's rational, mathematical beauty is beguiling to scientists. Fair enough, but for a theory to be a useful paradigm for describing reality, it must also display external consistency. Its assumptions and predictions must match observable phenomena. This is where the expanding universe theory falls short. It is not consistent with all that is the case in the universe. Anomalous data from James Webb are increasingly pressing against the dominant paradigm of astrophysics. James Webb, as you know, is the largest space telescope ever launched, is able to see back in time like never before thanks to a combination of its large mirrors and its sensitivity to infrared light. This means that it can see in stunning clarity objects whose light was emitted billions of years ago in the ultraviolet or visible portion of the spectrum, and has now been stretched by the universe's expansion to longer wavelengths than optical telescopes like Hubble. Astronomers are using it to peer back to near cosmic dawn, a time when the first stars and galaxies were forming. And the telescope is showing that these early galaxies are different than astronomers had anticipated, in a plethora of ways. Some are settling into shapes we didn't think were possible so early after the Big Bang. Others are unexpectedly large. As a result, over the past year, the press has been filled with news about phenomena that do not conform to the dominant paradigm. Very old galaxies that should not exist. In fact, exist. Galaxies nearly as massive as the Milky Way and full of mature red stars seem to be dispersed in deep field images obtained by James Webb during its observation campaign, and they are giving astronomers a headache. These galaxies, described in a study based on Webb's data release, are so far away that they appear only as tiny reddish dots to the powerful telescope. By analyzing the light emitted by these galaxies, astronomers established that they were viewing them in our universe's infancy just a few 100 million years after the Big Bang. Such early galaxies are not in themselves surprising. Astronomers expected that first star clusters sprung up shortly after the universe moved out of the so-called Dark Ages, the first 400 million years of its existence when only a thick fog of hydrogen atoms permeated space. But the galaxies found in the Webb images appeared shockingly big, and the stars in them too old. The new findings are in conflict with existing ideas of how the universe looked and evolved in its early years, and don't match earlier observations made by Webb's less powerful predecessor, the Hubble Space Telescope. As one of the authors of the study wrote, previous studies of the early universe with Hubble and other instruments tend to find small, blue baby galaxies at early times, objects which have just recently formed out of the primordial cosmic soup and are themselves building their early stars and structures. Young stars in general shine bright blue. With age, stars develop a redder glow as they burn through their fuel and cool down. In ancient galaxies that Webb was built to spot, astronomers had not expected to see old red stars. They also had not expected to find galaxies more massive than perhaps a billion suns. But those reddish dots revealed in Webb's deep fields appear 50 times more massive than that. This was astounding. We're finding galaxy candidates as massive as our own galaxy, when the universe was 3% of its current age. According to scientists, this is yet another big clue that the dominant paradigm about the universe expanding from a Big Bang is incorrect. The observations in the study mentioned is just one trickle in an increasing flow of data showing this. Astrophysics has many complexities, but one prediction of the expanding universe theory can be easily checked by observation, and thus the theory can be easily supported or defeated. The cosmologists tell us the universe is expanding. However, if the universe had been expanding for 12+ billion years, then we would see certain easily noticeable evidence. The expanding universe theory predicts that as space expands, the matter within space becomes less densely distributed, and galaxies become farther and farther apart. Introductory astronomy courses use a leavening ball of dough with raisins in it, raisin bread, to explain the theory. The claim is that every raisin is moving farther away from every other raisin, simple enough to understand. Logically, that means that as the loaf continues to rise, over time, the raisins will be further and further away from every other raisin. Therefore, as time goes by, the density of raisins within the loaf will decrease as the loaf expands, because the raisins will be spread more thinly. We see this phenomenon in rising bread dough, but do we see this in galaxies? The expanding universe theory predicts that, as time goes by, the density of galaxies within the universe will decrease as the universe expands, moving galaxies further and further away from each other, spreading them more thinly across space. The universe is billions of years old. It's not as simple as watching bread dough rise, but we can indeed look at galaxy density across both space and time to support or defeat the expanding universe theory. A light year is both a measure of time and distance. If an object is 1 light year away from us, then light takes 1 year to reach us. That means that the light we see is as the object was a year ago. So when astronomers talk about galaxies billions of light years away, they also mean their observations are of those objects as they were and where they were billions of years ago. The expanding universe theory says that as space expands, over time galaxies spread out and get farther from each other and become less densely packed in space. The theory predicts that we would see a lower density of galaxies 2 billion light years away than 8 billion light years away. If the universe had been expanding all that time, then the galaxies 8 billion light years away would, on average, be closer together than galaxies at a closer distance. It is simple to measure this, and measurements of galaxy distribution have been made. All surveys show that there is no significant change in the relative density of galaxy distribution across the universe, which means no difference over space or time. There is clumping in the universe where there are spots of greater matter density. However, the level of this clumping is the same at all distances. The density of galaxies in regions 8 billion light years away is not different from the density of galaxies in regions 2 billion light years away. Take any two distances, and the same is true. Thus, since distance in space equals distance in time, the observations confirm that the density of galaxies 8 billion years ago is not different from the density of galaxies 2 billion years ago. Therefore, we must conclude that the expansion theory is contradicted by the evidence. In other words, James Webb's unexpected findings have led some scientists to question the very fundamentals of the Big Bang theory and explore alternative explanations for the structure and evolution of the cosmos. Another profound question raised by James Webb's observations is the age of the stars within the distant galaxies. According to the Big Bang theory, the galaxies farthest away in the Webb images represent a cosmic snapshot from around 400 to 500 million years after the universe's birth. However, some of these galaxies appear to house stars that are over 1 billion years old. This presents a significant problem, as nothing should be older than the Big Bang itself. Furthermore, the abundance of galaxies, some as massive as the Milky Way, just a few 100 million years after the Big Bang, challenges the notion of a cosmic dark age as predicted by the theory. These discrepancies in age raise important questions about the origins and evolution of the universe. All of this beg the question: has James Webb disproven the Big Bang? Before answer this question, you should know that the Big Bang theory's predictions have been reliably wrong for decades. It's wrong about the cosmic microwave background, its temperature and smoothness, wrong about the scale of the largest structures in the universe, wrong about the abundance of lithium and helium, wrong about the size, age, and brightness of distant galaxies. But instead of abandoning the theory, cosmologists have modified it many times to fit what has already been observed and to smooth over previous contradictions as precisely as the emperor's new clothes. The classic standard model required two conceptual pieces. The first, as told, was the stage on which the drama of cosmology would play out, and it came in the form of Einstein's general theory of relativity. What we get from general relativity is a space-time that expands continuously, starting just after the Big Bang. Into that expanding space-time, the classic standard model then poured all the matter and energy described in another standard model, the one associated with particle physics. The central tenet of classic Big Bang cosmology was that the universe began as a super-hot, super-dense soup of fundamental particles. These particles were described in the standard model of particle physics and included things like quarks, electrons, photons, and other actors. Which particles you deal with depends on when you begin the story. As you go farther back in time, you run out of data from particle physics experiments to guide your descriptions. Using the standard model of particle physics, The classic version of the standard model of cosmology then follows the soup of particles and energy as the cosmos expands, cools, and thins out. The model made many predictions, but its first and most stunning validation came in 1964, when astronomers discovered the universe was filled with fossilized light left over from a few 100,000 years after the Big Bang. Cosmic microwave background radiation, or CMB, became one of cosmologists' most important resources in pushing the bounds of their understanding. In time, CMB introduced a number of problems or paradoxes to haunt the classic standard model. The most pressing of these was the smoothness of the background radiation. CMB looked the same no matter where astronomers directed their gaze. This implied conditions across widely separated regions of the early universe were identical. It was like looking at the weather to find every city on the planet had the exact same temperature. Either a miracle occurred in the early universe, or the cosmic microwave background's smoothness had a deeper explanation. Since physicists do not like miracles, they sought the deeper explanation. What they came up with in the 1980s was inflation. According to this new idea, very early in cosmic history, a tiny sliver of space-time underwent a brief period of tremendous expansion. That blown-up region of the cosmos became our visible universe. Inflation, driven by a hypothetical unknown quantum energy field, was so successful at accounting for CMB and the other paradoxes of the classic model that it became the base of the new, modern version of cosmology. As of today, all cosmology is inflationary cosmology. The revision did not end there. There were two other additions to the story. The first was the recognition that there was more matter out there than could be seen with telescopes. By tracking the motion of luminous matter, the stuff that emits light, astronomers had to admit that there seemed to be a whole lot more unseen or dark matter exerting a gravitational force. Whatever this dark matter was, it was not included in that standard model of particle physics. It was something new. While scientists could not directly see dark matter, confrontations between theory and observations told astronomers that whatever it was, this matter was not moving at relativistic speeds. It had to be slower-moving stuff. In other words, the dark matter was cold. Further observations showed that the dark stuff constituted the vast majority of cosmic matter. Somewhere around 85% of cosmic mass was dark. The second addition was another unseen player. Using distant supernovae, astronomers in the late 1990s discovered that the universe's expansion was accelerating. This meant the whole cosmos must be full of an invisible form of energy, and this energy was pushing space apart. This dark energy constituted a full 75% of the universe's total energy budget. Inflation, cold dark matter, and dark energy are key players in the modern version of cosmology's standard model. Sometimes called inflationary cosmology and sometimes labeled the LCDM model, this is the story every student must learn and master. What they also will learn is the remarkable concordance between the model and observations. On top of all the successes of the classic version of cosmology's standard model, the modern version matches key features of ultra-high-resolution maps of the CMB. It also explains features seen in the large-scale distribution of galaxies. Without doubt, the modern standard model of cosmology is a triumph of the scientific process. However, on the other hand, the Big Bang Theory is also kind of a kludge. The modern standard model seems to glue together a bunch of disparate parts without any overarching theoretical structure. Take inflation and dark energy. In both cases, we have a form of pervasive energy that pushes space apart. Inflation does it really fast and then dissipates. Dark energy does it much slower and does not dissipate. As far as we know, these forces have nothing to do with each other. Inflation was invented in the 1980s to solve a particular set of problems, especially CMB smoothness. Dark energy was added later on to solve another issue: cosmic acceleration. Likewise, dark energy and dark matter are in no way related, and they do not appear in the standard model of particle physics. The dark components were forced into the picture based on observations, but they don't fit into anything else we know. Add all this up, and there are reasons to wonder about the modern version of the standard model. It is impressive, and its accounts match up to lots of data with astonishing accuracy. But much of it also seems cobbled together out of necessity. It is not hard to imagine some future physicist laughing at the idea of dark matter or dark energy because some cleaner, simpler theory did away with them. So, is there such a theory out there waiting to be found? Is our standard model just a placeholder for something so different we won't even recognize the old ideas within the ideas yet to come? Only time will tell. Regardless, free and open debate is essential to obtaining scientific truth. It is long past time for cosmologists to throw off this self-censorship and say openly that the Big Bang and expansion theory may be entirely wrong. It is also way past time to stop ignoring the alternative, that the universe is evolving but not expanding, and that there was no hot, dense state of the cosmos nor an origin for the whole cosmos. Let's have that open debate begin in scientific publications and conferences and in the mass media. It looks like Eric Lerner have put on their life jackets on board the sinking cosmic ship Big Bang, but are not yet ready to enter the lifeboats. They should not hesitate further. A rescue ship, no Big Bang, is standing close by at the ready. Time to get on board and chart a new course for the science of the cosmos. As we delve deeper into the mysteries of the universe, we inevitably encounter the perplexing concept of time. We've learned lots of surprising and counterintuitive lessons from our investigations of time. Time is relative, not absolute. Time always marches forward, not backward, but we still lack an explanation for the arrow of time. Thermodynamically, the universe has an arrow of time, which flows in the same direction as increasing entropy. And when we investigate the universe on a fundamental level, it turns out that time may not be fundamental at all. But existence itself, it's very, very difficult to take that property away from time and to still wind up with a universe consistent with what we observe. However, it's worth noting that despite the popular trend to question the nature of time, its physical realness is not in doubt. Time is an integral part of the universe, and the boundary between events that have been observed or measured to have a definitive outcome and those whose outcome has not yet been decided is the best way we have to define precisely what we mean by the moment of now. As esteemed physicist Lee Smolin said, in the Copenhagen version of quantum mechanics, there is a quantum world and there is a classical world, and a boundary between them, when things become definite. When things that are indefinite in the quantum world become definite. Astronomers have long thought they understood how galaxies evolved. First, relatively small clusters of stars formed. These clusters then gathered together to produce baby galaxies. The baby galaxies then coalesced into the giant galaxies we see today. This process, from the first stars to near-mature galaxies, was expected to take about 1 billion years. Because our universe is about 14 billion years old, we needed a facility that could peer back in time and gather the data necessary to validate this theory. That's where the James Webb Space Telescope came in. James Webb Space Telescope is such an enigma that falls in the twilight zone where science fiction and reality meet. Without traveling so much as even a fraction of a second back in time, the $10 billion instrument is going to look at galactic events that happened millions of years ago. As fictitious as it may sound, it works on a very well-known principle. As we know, the speed of light and other electromagnetic waves is about 300,000 meters per second. Over a few thousand kilometers, such as those on Earth, it doesn't usually take light more than a microsecond to travel from one point to another. But in the vastness of the universe, where distances are colossal, light could even take years to travel. For instance, let's say you were observing a star in the night sky. Billions of miles away from its origin, at the surface of this star, light begins to travel and takes, say, 5 years to reach your eyes on Earth. Now, if this star were to die, its light would take 5 years to finally stop reaching you. In short, the farther away the object is, the more time light takes to travel, and the further back in its past we can see. The Webb telescope uses exactly this principle. It is equipped to be sensitive to particularly the longer wavelengths of light that have the capacity of traveling greater distances with minimal waning of brightness. So, to look at the farthest objects in the cosmic void, we must gather these wavelengths of light. In the electromagnetic spectrum, these are called the infrared rays and are associated with heat. It is here where the mind-bending design and build of the telescope comes into the picture. With its infrared eyes and its position far away in space, it's truly revealing the universe as we've only dreamed of seeing it, rife with tremendous advances and surprises. An enormous old galaxy. And most recently, James Webb has made unprecedentedly detailed observations of one of the earliest known galaxies, dubbed GZ9P3. Its name comes from the James Webb Space Telescope International Glass Collaboration and the fact the galaxy is at a redshift of Z equals 9.3, where redshift is one way to describe the distance to an object, hence G and Z 9P3. Just a couple of years ago, GZ9P3 appeared as a single point of light through the Hubble Space Telescope. But by using the James Webb Space Telescope, we could observe this object as it was 510 million years after the Big Bang, around 13 billion years ago. What's more, the team discovered that, much like other early galaxies seen by James Webb, GZ9P3 is far more massive and mature than expected for a galaxy in the infant universe. During the ancient time period in which it's been spotted, it already appears to contain several billion stars. When it comes to the cosmic conundrum of how early galaxies grew to become so massive so quickly, GZ9P3 could be a real puzzle. Not only is it more massive than expected, but it is around 10 times more massive than other galaxies James Webb has seen in similar eras of the universe's history. As Kit Boyette, team member and a scientist at the University of Melbourne, wrote for the Institute's Pursuit publication, just a couple of years ago, GZ9P3 appeared as a single point of light through the Hubble Space Telescope. But by using the James Webb Space Telescope, we could observe this object as it was 510 million years after the Big Bang, around 13 billion years ago. GZ9P3 is simply remarkable. Besides its size and maturity, its shape also reveals clues to its creation. Using James Webb and direct imaging, the team was able to determine that GZ9P3 has a complex shape with 2 bright patches that reveal its 2 dense nuclei. That indicates GZ9P3 was likely created when 2 early galaxies smashed together in the infant universe. This collision may have still been ongoing during the time at which astronomers noticed GZ9P3 with the Webb telescope. As Boyette explained, the James Webb imaging of the galaxy shows a morphology typically associated with 2 interacting galaxies, and the merger hasn't finished because we still see 2 components. When 2 massive objects join like this, they effectively throw away some of the matter in the process. So, this discarded matter suggests what we observed is one of the most distant mergers ever seen. In addition to determining the age, mass, and shape of this ancient galaxy, Boyette and colleagues were able to probe deeper within GZ9P3 to examine the stellar population of these colliding galaxies. Because young stars are brighter than their older counterparts, they usually dominate galaxy images, especially those that are so distant their light has been traveling to Earth for billions of years. For example, a young bright population sparked by the galaxy merger, less than a few million years old, outshines an older population already over 100 million years old. The glass collaboration worked around this by taking spectroscopic observations of GZ9P3 as well as by tapping into direct imaging. Spectroscopy can be used to determine the elements that make up stars. Because young and old stars have different compositions, this allowed the researchers to separate the two categories in this early galaxy. Older stars have worked their way through the hydrogen supply in their cores, having already fused it all into helium, and then fusing this helium to create even heavier elements, which astronomers call metals. This means older stars are richer in metals than younger stars, which are still dominated by hydrogen and some helium. The study team used James Webb to detect specific elements in the older star population of GZ9p3. These target elements included silicon, carbon, and iron, the latter of which is the heaviest element that can be synthesized by stars. This means these stars, when they died in supernova explosions, would have enriched the early universe with metals. Much of this metal content would have gone on to become the building blocks of the next generation of stars. In addition, the team discovered that the population of old stars in GZ9p3 was much larger than previously suspected. This means that, while astronomers have been aware of this cycle of stellar life and death and the increasing metal enrichment of subsequent generations of stars, the GZ9p3 observations indicate galaxies may have become chemically mature faster than had been suspected previously. These observations provide evidence of a rapid, efficient buildup of stars and metals in the immediate aftermath of the Big Bang, tied to ongoing galaxy mergers, demonstrating that massive galaxies with several billion stars existed earlier than expected. Galaxies that sit isolated from their galactic counterparts do form stars, but the process is slow and ends when that galaxy exhausts its reservoir of gas and dust, the materials that form stars. For galaxies close to each other, the process of star formation can be sped up and even revived after it has drawn to a halt. That's because when these galaxies are drawn together by a mutual gravitational attraction, they collide. The merger then causes an inflow of fresh gas that kickstarts a period of rapid star birth called a starburst. Meaning mergers provide an excellent way for galaxies to rapidly grow their stellar populations. Most large galaxies in the universe have grown this way. Our own galaxy, the Milky Way, shows a history of mergers itself. For instance, it has been involved in the cannibalization of smaller satellite galaxies that once orbited it. The Milky Way currently forms stars at a stunted rate, but this will change when it collides with our neighboring galaxy, Andromeda, in around 4.5 billion years. This will cause an influx of gas that kicks off a fresh bout of starburst. Thanks to observations of GZ9p3, astronomers are getting the message that this channel for rapid mass accumulation and star birth was a bigger factor in the early universe than predicted. As Boyette explained, these observations of GZ9p3 show that galaxies were able to accumulate mass quickly in the early universe through mergers, with star formation efficiencies higher than we expected. This and other observations using the James Webb Space Telescope are causing astrophysicists to adjust their modeling of the early years of the universe. Our cosmology isn't necessarily wrong, but our understanding of how quickly galaxies formed probably is, because they are more massive than we ever believed could be possible. A collection of ancient galaxies transformed the entire universe. But while James Webb has created more and more puzzles, it also solves a lot. Another new observations with the James Webb Space Telescope has just revealed collection of ancient galaxies that packed a massive punch, shaping the entire universe when it was less than 1 billion years old. The international team found the galaxies, which resemble dwarf galaxies that exist today, played a vital role during a crucial stage of cosmic evolution that occurred between 500 and 900 million years after the Big Bang. These small galaxies also vastly outnumbered larger galaxies in the infant universe, the scientists say, adding that it's likely the realms supplied most of the energy needed for a process called cosmic reionization. Cosmic reionization was critical to the growth and progression of the universe. As Hakim Atek, Research lead author and an astronomer at the Institut d'Astrophysique de Paris said, "We're really talking about the global transformation of the entire universe. The main surprise is that these small, faint galaxies had so much power, their cumulative radiation could transform the entire universe." Prior to around 380 million years after the Big Bang happened, during a period called the Epoch of Recombination, the now 13.8 billion-year-old universe had been opaque and dark. This was because, in its dense and ultra-hot state, free electrons endlessly bounced around particles of light, called photons. However, later, during the Epoch of Recombination, the universe had expanded and cooled enough to allow electrons to bond with protons and create the first atoms of hydrogen, the lightest and simplest element in the cosmos. This disappearance of free electrons meant photons were suddenly free to travel, and as a result, the dark age of the universe ended. The cosmos suddenly became transparent to light. This first light can be seen today in the form of a cosmic fossil that uniformly fills the universe called the cosmic microwave background, or CMB. Because electrons and protons have equal but opposite electric charges, these first atoms were electrically neutral, but they would soon undergo yet another transformation. After 400 million years, the first stars and galaxies formed. Then, during the era of reionization, neutral hydrogen, the predominant element in the universe, was transformed into charged particles. These particles are called ions. Ionization is caused by electrons absorbing photons and increasing their energy, breaking free from atoms. Until now, scientists weren't sure where this ionizing radiation came from. Suspects for the radiation source behind reionization had included supermassive black holes feeding on gas from accretion disks surrounding them, causing these regions to eject high-energy radiation. Large galaxies with masses in excess of 1 billion suns, and smaller galaxies with masses less than this. But identifying smaller dwarf galaxies as main sources of this ionizing radiation was a challenge for a long time because of how faint they are. Luckily, the Webb telescope has spectroscopic capabilities in the infrared, and in fact, one of the reasons we built the observation is to understand what happened during the epoch of reionization. But noting that even with the impressive infrared observing power of James Webb, spotting these dwarf galaxies wouldn't have been possible without the help of Albert Einstein. More specifically, without the help of his 1915 theory of general relativity and an effect on light it predicts. General relativity suggests all objects of mass warp the very fabric of space and time, which are, in truth, united as a single entity called space-time. Our perception of gravity, the theory says, arises as a result of that curvature. The greater the mass of an object, the more extreme the curvature of space-time is. Thus, the stronger its gravitational effects are. Not only does this curvature tell planets how to move in orbits around stars, and in turn, tell those stellar bodies how to orbit the supermassive black holes at the centers of their home galaxies, but it also changes paths of light coming from the stars. Light from a background source can take different paths around a foreground object as it travels toward Earth, and the closer that path is to an object of great mass, the more it gets bent. Thus, light from the same object can arrive to Earth at different times as a result of the foreground, or lensing, object. This lensing can shift the location of the background object in the sky, or it can cause the background object to appear in multiple places in the same image of the sky. Other times, light from the background object is amplified, and thus that object is magnified in the sky. This effect is known as gravitational lensing, and James Webb has been using it to great effect to observe ancient galaxies near the dawn of time, which it would otherwise have had no chance of seeing. To observe the newly studied distant and early dwarf galaxies and analyze the light they emit, James Webb used a galaxy cluster called Abell 2744 as a gravitational lens. With the mystery of reionization potentially solved, the team now aims to extend this study to a larger scale with another Webb's project called Glimpse. The researchers will first try to confirm that the particular location studied in this research is representative of the average distribution of galaxies in the universe. Then, beyond studying the reionization process, ATEC and colleagues will aim to better understand the formation of the very first galaxies, which, over the course of 12 billion years, grew into present-day galaxies, evidence for the first generation of stars. A piece of good news, evidence for the first generation of stars to exist in the universe has come to light thanks to observations made by James Webb. The proof is located in one of the most distant galaxies known. The galaxy, designated GNZ11, was discovered by the Hubble Space Telescope in 2015, and prior to the launch of the James Webb Space Telescope, it was considered the most far-away galaxy known. With a redshift of 10.6, it makes more sense to talk about how long ago it existed rather than how far away it is. That's because we see GNZ11 as it was just 430 million years after the Big Bang due to the time it took for its light to travel to our corner of the cosmos. For comparison, the universe today is 13.8 billion years old. As such, GNZ11 was a prime target for James Webb to study. Now, 2 new papers describe profound discoveries about GNZ11 that reveal vital details about how galaxies that existed in the early universe were able to grow. GNZ11 is the most luminous galaxy known at this particular redshift, and indeed, this has become a common theme for high redshift galaxies, now almost regularly being found in the early universe by James Webb. Many of them appear much brighter than what our models of galaxy formation predict they should be. Those predictions are based on the standard model of cosmology. Now, Webb's new observations seem to have shed light on what is going on. An astronomy team, led by Roberto Maiolino of the University of Cambridge, has probed GNZ11 with Webb's 2 near-infrared instruments, the NIR-CAM and the NIR-SPEC. The researchers discovered evidence for the first generation of stars, called population 3 stars, as well as for a supermassive black hole gobbling up huge amounts of matter and growing at a vastly accelerated rate. Scientists can calculate the age of a star based on its abundance of heavy elements, which would have been formed by previous generations of stars that lived and died, spewing those heavy elements into space where they ultimately get recycled in star-forming regions to form new stellar bodies. The youngest stars that have formed during the past 5 or 6 billion years are referred to as population 1 stars and have the highest abundance of heavy elements. Our Sun is a population 1 star. Older stars contain fewer heavy elements because there had been fewer generations of stars before them. Older stars contain fewer heavy elements because there had been fewer generations of stars before them. We call these population 2 stars, and they live in the oldest regions of our Milky Way galaxy. However, population 3 stars have been purely hypothetical up until now. These would have been the first stars to form, and because no other stars came before them, they would have contained no heavy elements and be made from only the pristine hydrogen and helium forged during the Big Bang. These first stars are also thought to have been extremely luminous, with masses equal to at least several hundred suns. Although astronomers still haven't seen population 3 stars directly, Maiolino's team detected indirect evidence for them in GNZ11. NIR-SPEC observed a clump of ionized helium near the edge of GNZ11. This helium gas is being ionized by something that's producing huge amounts of ultraviolet light, with that something inferred as the population 3 stars. Potentially, the helium witnessed is leftover material from those stars' formation. The amount of ultraviolet light required to ionize all that gas requires about 600,000 solar masses of stars in total, shining with a combined luminosity 20 trillion times brighter than our Sun. These figures suggest distant galaxies, such as GNZ11, would have been more adept at forming massive stars than galaxies in the modern universe. Meanwhile, according to a second set of results, Maiolino's team also found evidence for a 2 million solar mass black hole at the heart of GNZ11. Specifically, they found extremely dense gas that is common in the vicinity of supermassive black holes accreting gas. These were the first clear signatures that GNZ11 is hosting a black hole that is gobbling matter. The team also detected a powerful sleet of radiation flowing off the accretion disk of matter swirling around the black hole, as well as ionized chemical elements typically found near accreting black holes. It is the most distant supermassive black hole discovered so far, the team says, and its gluttonous appetite leads to its accretion disk becoming dense and hot and shining brightly. This, combined with the population 3 stars, is what makes GNZ11 shine so brightly, the researchers believe, without breaking standard cosmology as some have prematurely claimed. An extremely red, supermassive black hole growing in the early universe. Elsewhere, using the James Webb Space Telescope, astronomers have discovered an extremely red supermassive black hole growing in the shadowy early universe. The red hue of the supermassive black hole, seen as it was around 700 million years after the Big Bang, is the result of the expanding universe. As the universe balloons outward in all directions, light traveling toward us gets redshifted, and the redshifted light, in this case, indicates a cloak of thick gas and dust shrouding the black hole. Examining Webb's data, the astronomy team led by Lucas Furtak and Adi Zitrin of the Ben-Gurion University of the Negev was also able to determine the mass of the supermassive black hole. At around 40 million times the mass of the Sun, it is unexpectedly massive in comparison to the galaxy in which it resides. The team also found that the supermassive black hole, which is located around 12.9 billion light-years away from Earth, is rapidly feasting on the gas and dust around it. In other words, it's growing. As Furtak said in a statement, 3 very compact yet red-blooming objects prominently stood out and caught our eyes. Their red dot appearance immediately led us to suspect that it was a quasar-like object. Quasars are created when copious amounts of matter surround supermassive black holes like this one. This matter forms a disk of gas and dust called an accretion disk that gradually feeds the black hole. The immense gravitational influence of the black hole churns this matter, generating intense temperatures and causing it to glow. Additionally, matter that doesn't fall into the supermassive black hole is channeled to the cosmic titan's poles. Particles in these regions are accelerated to speeds approaching that of light as highly collimated jets. As these relativistic jets are blasted out, the eruptions are accompanied by bright electromagnetic emissions. As a result of these phenomena, quasars powered by supermassive black holes in active galactic nuclei are often so bright that the light they emit often outshines the combined light of every star in the galaxy that surrounds them. The vast amount of radiation being emitted from around this particular supermassive black hole caused it to take on a small, point-like appearance in Webb's data. Analysis of the object's colors indicated that it was not a typical star-forming galaxy. This further supported the supermassive black hole hypothesis. Together with its compact size, it became evident this was likely a supermassive black hole, although it was still different from other quasars found at those early times. But noting that the early quasar wouldn't have been visible even to the powerful infrared eye of James Webb without a little help from an effect predicted by Albert Einstein in 1915. In this case, the Webb telescope used a galaxy cluster called Abell 2744 as a foreground lensing body to amplify light from background galaxies, which are otherwise too distant to see. This revealed the extremely red quasar they zeroed in on, originally in the form of 3 red dots. Further analysis of the background source revealed its light must have come from a compact region. According to team member and Princeton University researcher Jenny Green, All the light of that galaxy must fit within a tiny region the size of a present-day star cluster. The gravitational lensing magnification of the source gave us exquisite limits on the size. Even packing all the possible stars into such a small region, the black hole ends up being at least 1% of the total mass of the system. The discovery further adds to the mystery of how supermassive black holes, which can be millions or even billions of times as massive as the Sun, grew to such huge sizes during the universe's infancy. And as told, James Webb has detected a wealth of little red dots over time. These could also indicate feeding supermassive black hole-powered quasars in the early universe, maybe meaning a striking black hole growth conundrum could soon be solved. In a way, it's the astrophysical equivalent of the chicken and egg problem. We do not currently know which came first, the galaxy or black hole, how massive the first black holes were, and how they grew. When it comes to the science of cosmology, one of the crowning achievements of the past 100 years is the development of a standard model of cosmology. The dominant factor in determining how the universe evolves is gravitation, which is governed by general relativity and accounts for the expanding universe as well as the assembly of large-scale cosmic structures. The contents of the universe have been determined to be dark energy, dark matter, normal matter, neutrinos, and photons. And the universe as we know it began some 13.8 billion years ago, with an event known as the Hot Big Bang, with density imperfections seeded by a preceding phase known as cosmic inflation. Despite all the observational evidence we have supporting this picture, it may not be fully correct. Each time we observe the universe in a new way, we have to check that what we're seeing is still consistent with this model. With the addition of James Webb to the arsenal of tools astronomers have, is this picture in trouble? The answer would seem to be yes. So, is it time to dethrone the Big Bang Theory? Well, this topic remains controversial among scientists, as some think we need to rewrite all the textbooks while others think that our current model just needs some updates as it had been. So, who's right? All this and more will be discussed in today's episode. The first thing we have to do is lay out how we expect events to unfold in our universe based on our current picture of the universe. This picture, sometimes called the Standard Model of Cosmology, sometimes called the Inflationary Hot Big Bang, and sometimes called Lambda Cold Dark Matter, or LCDM model, has been remarkably successful explaining features ranging from the internal motions of individual galaxies, the motions of galaxies relative to one another, the motions of galaxies within groups and clusters of galaxies, weak and strong gravitational lensing on all cosmic scales, the structure and growth of the cosmic web, and the features found in the Big Bang's leftover glow, the cosmic microwave background. It also predicts that, as we look farther and farther back in time, that is to greater and greater cosmic distances, that the galaxies we see will be inherently smaller, bluer, less evolved, less rich in heavy elements, and that at some point beyond where we've been able to look, we should cease to see stars or galaxies of any type, as we'll reach the universe's dark ages. But that's simply a picture of what happens. What we need, if we want to compare theory to observations, is to quantitatively figure out not just what happens, but when it happens, and quantitatively, how much it happens by. Even though the laws of physics are well known, and the starting point, or our initial conditions, are also well known, our best quantitative predictions still come along with a large amount of uncertainty. From the theory of cosmic inflation and the patterns of fluctuations that we see in the cosmic microwave background, we know that our universe began at the start of the Hot Big Bang, from an almost perfectly uniform state. There were the seeds of structure, density imperfections, imprinted atop that near-uniform background, leading to underdensities and overdensities at about the 1 part in 30,000 level, that were almost but not quite the same on all cosmic scales, about 3% larger on size of the universe scales than on size of a galaxy scales. We know that early on, these imperfections grew gravitationally, but also had to contend with interactions with and pressure from radiation, like photons, creating a pattern of peaks and valleys in how overdense, underdense various regions were on a variety of cosmic scales. Then, the universe forms neutral atoms about 380,000 years after the hot Big Bang, and expands, cools, and gravitates according to the laws of general relativity. As long as these density imperfections remain small compared to the average density of the universe, it's easy and straightforward to compute how they grow. But as they grow larger, a series of effects all come into play, making the question of how big do they grow and how quickly very assumption dependent. For example, as large amounts of gas begin to accrue in these overdense regions, how efficiently does that gas cool? As these overdense regions grow within the expanding universe, with some small-scale regions superimposed atop larger-scale overdensities, how do these high-density regions interact in these overlapping locations? Some overdense regions will occur close to other overdense regions. How is the growth of structure affected when these regions interact? As normal matter accumulates in the centers of these overdense regions, it slows down, collides, and heats up. As that heat gets radiated away, how does that feedback affect the growth rate of these regions, including both the normal matter and the dark matter? And finally, when stars finally form in these very different environments to the ones we find today, how long do they live? How do they die? How does that impact the normal and dark matter that doesn't become stars? And what implications does that have for subsequent generations of stars and the growth of these early cosmic structures? It's important to understand that the answers to all of these questions are uncertain. They're firmly in the realm of the purely theoretical and are dependent on what details we include and exclude in our models and simulations. Are we using the correct models to identify halos, where a halo represents an individual overdensity in space? Or are we incorrectly treating interdependent halos as independent entities or vice versa? Are we modeling the first stars correctly, including their initial mass functions and their death throes? Or are they heavier and more likely to directly collapse to black holes than we think? For that matter, do we even need stars to form black holes? Or can these intersecting, inflowing streams of gas form the seeds of supermassive black holes directly, possibly with masses that are 10,000 plus times the mass of our sun right away? It's pretty clear that the very first objects, stars, black holes, and star clusters, begin forming no later than about 150 million years after the Big Bang, and perhaps as early as only 50 to 100 million years after the Big Bang. But these ought to be relatively rare occurrences. Bright, evolved galaxies we should see at slightly later times, like 200, 300, or 400 million years after the Big Bang, is a much murkier question. But we don't simply have our theoretical expectations, even with the appropriate uncertainties, to work off of. For the first time, owing to the unprecedented capabilities of the James Webb Space Telescope, we're beginning to discover and characterize galaxies found in these very, very early stages of our cosmic history. Scientists expected this observation find some small blue baby galaxies at early times, objects which have just recently formed out of the primordial cosmic soup and are themselves building their early stars and structures. However, contrary to all expectations, right from the very first images sent back by the James Webb Telescope, we are already confronted with galactic behemoths, giants that simply could not have formed in the time allotted to them in the established theory of the Big Bang. According to preliminary analysis, these galaxies formed just 300 million years after the Big Bang. By comparison, our planet is 4.5 billion years old, and it takes 200 million years for our galaxy, the Milky Way, to complete just one rotation. The classical theory of galaxy development cannot explain how these galaxies might have formed in such a short time. And this is just the beginning. Astronomers have always thought that galaxies couldn't have gotten very big so early in the universe's history, and would start bulking up on stars about 500 million years out from the Big Bang. But Webb galaxies are extremely luminous, suggesting that it holds an abundance of stars, which together are 1 billion times as massive as our Sun. In other words, the most massive galaxies in our sample are estimated to have masses 2 to 4 times lower than that of our own Milky Way. This was astounding. We're finding galaxy candidates as massive as our own galaxy when the universe was 3% of its current age. What's notably, it isn't just the size of these galaxies that poses a problem to the established theory. So too does their composition. The stuff they are made of typically suggests it has been recycled over many generations of star formation. Big Bang theorists calculate that after the initial explosion that created the universe, all that existed was hydrogen and helium and tiny amounts of heavier elements. In other words, such young galaxies are dust-poor. However, we already find around 20% of the galaxies that assembled during this early epoch are already very dusty, and a significant fraction of the ultraviolet light from newborn stars is already hidden by this dust. That, put simply, broke the Big Bang model of cosmology. But the question of galaxy formation, enormous agglomerations of swirling gas, dust, and stars, is only the tip of the iceberg. Observational astronomy has uncovered far, far larger structures that completely confound Big Bang cosmologists. According to the assumptions that form part of Big Bang cosmology, no cosmic object can be more than 250 million light-years wide. And yet every year, astronomers are discovering larger and larger megastructures that are billions of light-years wide. For instance, early this year, scientists have spotted a second ultra-large structure dubbed the Big Ring that challenged long-held assumptions about the universe's structure. Situated 9.2 billion light-years away from Earth, the Big Ring is also creating problems for the current understanding of the basic principles of cosmology. The colossal structure boasts a diameter of about 1.3 billion light-years and a circumference of nearly 4 billion light-years. To put its enormity into perspective, if visible, the Big Ring would span an area of the sky equivalent to 15 full moons. And of course, this is not our first discovery of a massive cosmic mystery. 2 years prior, we discovered the Giant Arc, another megastructure measuring 3.3 billion light-years across. Both the Big Ring and the Giant Arc reside in the same cosmic neighborhood, observed at an identical distance and era in the universe's timeline, merely 12 degrees apart in the sky. But neither of these two ultra-large structures is easy to explain in our current understanding of the universe. Their ultra-large sizes, distinctive shapes, and cosmological proximity must surely be telling us something important. But what exactly? We just don't know. Regardless, there is no doubt that James Webb will continue to discover other mammoth structures, and perhaps some that loom even larger than the Giant Arc. Light itself would take billions of years to traverse such a structure. The freefall collapse of matter under gravity would have taken eons. These discoveries are weighing down on the Big Bang theory. There is only so long that the theory's defenders can continue moving the goalposts in the manner that they have done for decades to force observations to fit their preconceived view. Genuine science progresses as theories are devised to explain our observations. An accumulation of inexplicable observations at a certain stage demands the revision of a theory. Certainly, there is a disconcerted mood among astronomers. "Panic," reads the title of one pre-publication paper. Alison Kirkpatrick of the University of Kansas tweeted, "Right now, I find myself lying awake at 3 in the morning and wondering if everything I've done is wrong." However, the consciousness of the elites of the scientific community is quite conservative. Therefore, rather than question the underlying theory, the theory of Big Bang cosmology, they are denying galaxies their infancy. Given the evidence of galaxies almost as old as the universe itself, proponents of the Big Bang assume that early galaxies formed faster than initially theorized. There is no reason to assume that the history of the local universe was not punctuated by periods of sudden development. There may well have been one or more booms of galaxy formation. The universe abounds in abrupt and sudden dialectical processes. However, the attempts to adjust the birth rates of galaxies have less to do with explaining the birth of galaxies and everything to do with saving a theory that is quickly coming into question in the light of new discoveries. Big Bang cosmology, as we know, has suffered many such adjustments in its history. This cosmological theory originates from perhaps the most absurd extrapolation in the history of science. In the 1920s, the astronomer Edwin Hubble discovered that the further a galaxy is from us, the redder it appears. This reddening can be explained by referring to something known as the Doppler effect, whereby the light spectra of objects moving away from us appear redder. From this, astronomers concluded that the observable universe appears to be expanding. However, this was drawn to its extreme and absurd conclusion. If everything is moving away from everything else, at some time in the history of the universe, all matter must have been in a single point, which the defenders of the Big Bang call a singularity, no bigger than a single hydrogen atom. At that time, not only did all matter and energy come into existence, but the very fabric of space and time supposedly came into being too. But the Doppler shift is, at best, evidence of the expansion of a sector of the universe, not of a singular and absolute beginning to time and space. Here we have an unfortunate example of a fact being pushed to its absurd limit and literally making a cosmic leap. The Big Bang is not so much a matter of scientific evidence, but of the philosophical interpretation of the evidence. That a part of the universe within our narrow horizon appears to be expanding does not authorize us to affirm that the entire universe is doing so. Even less can we extrapolate from this fact that all of this results from a point of singularity where space and time mystically came into existence. Some deny that the Big Bang means a beginning to time. They claim Big Bang cosmology merely postulates that the universe existed in a hot, dense state in the past. But prominent modern cosmologists do in fact defend a beginning to time. As Stephen Hawking explained, the universe has not existed forever. Rather, the universe and time itself had a beginning in the Big Bang. The beginning of real time would have been a singularity at which the laws of physics would have broken down. Frankly, alternative Big Bang theories that attempt to avoid a singularity are no less speculative or absurd than the notion of a singularity. The astronomer who first proposed the Big Bang hypothesis in the 1920s, Georges Lemaitre, certainly had no problem with the idea that cosmic redshift somehow proves that the universe was created ex nihilo. This was because, being an ordained priest, it was obvious to him how a universe can be created from nothing. It was brought into being by God, the Creator. Lemaitre won the effusive laurels of the Vatican for this contribution to the faith. Nevertheless, it may seem impressive that this theory, first proposed in the 1920s, has survived the test of observational astronomy for a whole century. But the Big Bang theory as it exists today bears only a passing resemblance to Lemaitre's original hypothesis, precisely because of its repeated failure to tally with observational findings. The only observational success of Big Bang cosmology in the last century was a truly revolutionary discovery in 1964. Two astronomers, Robert Wilson and Arno Penzias, were using a radio telescope designed to examine satellite communications. They encountered a strange phenomenon. When they directed their telescope at any point in the sky, they found a weirdly persistent microwave signal. There was no point in the sky from which this signal did not emanate. They began to look closely at the idea that the universe had been very different in the past than it was now. This was implied by Lemaitre's idea and had been picked up in the early 1950s by two physicists, Ralph Alpher and George Gamow. Alpha and Gamma were building a model of cosmic history where the universe began in an incredibly hot, dense state. Gamma's models predicted that approximately 300,000 years after the universe started expanding, space filled with a particular kind of electromagnetic radiation as matter particles cooled and changed their interactions. Not only that, this radiation would persist forever, a kind of fossil light. And it was this fossil light that Wilson and Penzias inadvertently picked up in their radio telescope. All the pieces of the jigsaw were perfectly slotting together. Wilson and Penzias had made an insurmountable breakthrough. The universe did indeed have a history. It had once expanded from a type of primeval atom, and it had continued to expand since. In doing so, it had left behind traceable electromagnetic emissions, which silently polluted the sky, invisibly goading desperate researchers, waiting to be found by technology that was advanced enough. This discovery, known in scientific circles as cosmic microwave background radiation, established cosmology as a science and the Big Bang theory as the foundation for all explorations of cosmic evolution. Since then, observations have further supported its veracity, and more details have bulked out the theory. Over the past 60 years, cosmology has become ever more precise in its ability to account for the best available data about the universe. But along the way, to gain such a high degree of precision, astrophysicists have had to postulate the existence of components of the universe for which we have no direct evidence. The standard model today holds that normal matter, the stuff that makes up people and planets and everything else we can see, constitutes only about 4% of the universe. The rest is invisible stuff called dark matter and dark energy, roughly 27% and 68%. Cosmic inflation is an example of yet another exotic adjustment made to the standard model. Devised in 1981 to resolve paradoxes arising from an older version of the Big Bang, the theory holds that the early universe expanded exponentially fast for a fraction of a second after the Big Bang. This theory solves certain problems but creates others. Notably, according to most versions of the theory, rather than there being one universe, ours is just one universe in a multiverse, an infinite number of universes, the others of which may be forever unobservable to us, not just in practice, but also in principle. There is nothing inherently fishy about these features of the standard model. Scientists often discover good indirect evidence for things that we cannot see, such as the hyperdense singularities inside a black hole. But in the wake of the Webb's confounding data about galaxy formation and the worsening problem with the Hubble constant, you can't be blamed for starting to wonder if the model is out of joint. A familiar narrative about how science works is often trotted out at this point to assuage anxieties. It goes like this. Researchers think they have a successful theory, but new data show it is flawed. Courageously rolling up their sleeves, the scientists go back to their blackboards and come up with new ideas that allow them to improve their theory by better matching the evidence. It's a story of both humility and triumph, and we scientists love to tell it. And it may be what happens in this case too. Perhaps the solution to the problems the Webb is forcing us to confront will require only that cosmologists come up with a new, dark something or other that will allow our picture of the universe to continue to match the best cosmological data. However, there is another possibility. We may be at a point where we need a radical departure from the standard model, one that may even require us to change how we think of the elemental components of the universe, possibly even the nature of space and time. Cosmology is not like other sciences. It's not like studying mice in a maze or watching chemicals boil in a beaker in a lab. The universe is everything there is. There's only one, and we can't look at it from the outside. You can't put it in a box on a table and run controlled experiments on it. Because it is all-encompassing, cosmology forces scientists to tackle questions about the very environment in which science operates, the nature of time, the nature of space, the nature of law-like regularity, the role of the observers doing the observations. These rarefied issues don't come up in most regular science, though one encounters similarly shadowy issues in the science of consciousness and in quantum physics. Working so close to the boundary between science and philosophy, cosmologists are continually haunted by the ghosts of basic assumptions hiding unseen in the tools we use, such as the assumption that scientific laws don't change over time. But that's precisely the sort of assumption we might have to start questioning in order to figure out what's wrong with the standard model. One possibility, raised by the physicist Lee Smolin and the philosopher Roberto Mangabeira Unger, is that the laws of physics can evolve and change over time. Different laws might even compete for effectiveness. An even more radical possibility, discussed by the physicist John Wheeler, is that every act of observation influences the future and even the past history of the universe. It is not obvious, to say the least, how such revolutionary reconsiderations of our science might help us better understand the cosmological data that is flummoxing us. It would necessarily be a leap of faith to step back and rethink such fundamentals about our science. But a revolution may end up being the best path to progress. That has certainly been the case in the past with scientific breakthroughs like Copernicus's heliocentrism, Darwin's theory of evolution, and Einstein's relativity. All three of those theories also ended up having enormous cultural influence, threatening our sense of our special place in the cosmos, challenging our intuition that we were fundamentally different than other animals, upending our faith in common-sense ideas about the flow of time. Any scientific revolution of the sort we're imagining would presumably have comparable reverberations in our understanding of ourselves. As Geraint F. Lewis, professor of astrophysics at the Sydney Institute for Astronomy, part of the University of Sydney's School of Physics, said, "Sometimes, a new idea completely overturns the way we look at the cosmos." Einstein, Lemaitre, Friedman, Hubble, and others showed that our universe is not static, but expanding. Throughout the 20th century, astronomers mapped out our location among the stars of our galaxy and our galaxy's place in the cosmos. Maybe we've got the picture roughly correct, or maybe we're just waiting for the next Newton or Einstein to show us an even grander picture of the physical universe. To do this, we also need new instruments. Luckily, astronomy has a bright future. We are about to have the Habitable Worlds Observatory, a Hubble Space Telescope on steroids that will see Earth like exoplanets around Sun like stars. We are about to have a Far Infrared Observatory, the Origins Space Telescope, to detect molecules in cold, dusty objects and see stars and planets forming. And one day, we will have the Lynx X-ray Observatory, to understand extreme temperatures around black holes and explosions of all sorts. In addition to new telescopes, we have new computing tools. We can already make movies of the history of the universe based on hypothetical initial conditions and the laws of physics, just as we can predict the weather with hydrodynamic codes. These simulations are limited. As objects evolve and become smaller and hotter, the computation to describe them becomes too difficult to include in the original simulations. But AI may allow us to overcome this by reducing the computation necessary to get good results. Jumping ahead, I see no law of nature preventing artificial general intelligence, a form of AI that truly understands the words it uses to talk with us. Given the billions of dollars being spent every year and the immense motivations leading to those budgets, I think it's only a matter of time. We don't have to understand how it works to use it. We don't understand the human mind either. Be ready to be amazed. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.
We are going to be able to answer questions that we don't even know what the questions are yet. This is what's happening.
For years, the Big Bang Theory is known as the leading explanation for how the universe began. It is the idea that the universe began as just a single point, then expanded and stretched to grow as large as it is right now, and it is still stretching. But recently, this belief has been somewhat shaken as images taken by the James Webb Space Telescope contradicted the Big Bang Theory. When NASA's time machine first opened its eyes and peered into the deep universe, it captured the unimaginably distant universe shocked astronomers. Could the bevy of anomalously big and bright early galaxies be illusory? Perhaps because of flaws in analysis of the telescope's initial observations? If genuine, could they somehow be explained by standard cosmological models? Or, just maybe, is the Big Bang and all of modern cosmology in trouble? Join us as we dig into the origins of the universe. The first thing we have to do is lay out, based on our picture of the universe, how we expect events to unfold in our universe. This picture, sometimes called the Standard Model of Cosmology, sometimes called the Inflationary Hot Big Bang, and sometimes called LCDM, Lambda Cold Dark Matter Model, has been remarkably successful, explaining features ranging from the internal motions of individual galaxies, the motions of galaxies relative to one another, the motions of galaxies within groups and clusters of galaxies, weak and strong gravitational lensing on all cosmic scales, the structure and growth of the cosmic web, and the features found in the Big Bang's leftover glow, the cosmic microwave background. It also predicts that as we look farther and farther back in time, i.e., to greater and greater cosmic distances, that the galaxies we see will be inherently smaller, bluer, less evolved, less rich in heavy elements, and that at some point beyond where we've been able to look, we should cease to see stars or galaxies of any type, as we'll reach the universe's dark ages. But that's simply a picture of what happens. What we need, if we want to compare theory to observations, is to quantitatively figure out not just what happens, but when it happens, and quantitatively how much it happens by. Even though the laws of physics are well known, and the starting point, or our initial conditions, are also well known, our best quantitative predictions still come along with a large amount of uncertainty. From the theory of cosmic inflation and the patterns of fluctuations that we see in the cosmic microwave background, we know that our universe began at the start of the hot Big Bang, from an almost perfectly uniform state. There were the seeds of structure, density imperfections, imprinted atop that near uniform background, leading to underdensities and overdensities at about the 1 part in 30,000 level, that were almost, but not quite, the same on all cosmic scales, about 3% larger on size of the universe scales than on size of a galaxy scales. We know that early on, these imperfections grew gravitationally, but also had to contend with interactions with and pressure from radiation, like photons, creating a pattern of peaks and valleys in how overdense or underdense various regions were on a variety of cosmic scales. Then, the universe forms neutral atoms about 380,000 years after the hot Big Bang, and expands, cools, and gravitates according to the laws of general relativity. As long as these density imperfections remain small compared to the average density of the universe, it's easy and straightforward to compute how they grow. But as they grow larger, a series of effects all come into play, making the question of how do they grow and how quickly very assumption dependent. For example, As large amounts of gas begin to accrue in these overdense regions, how efficiently does that gas cool? As these overdense regions grow within the expanding universe, with some small-scale regions superimposed atop larger-scale overdensities, how do these high-density regions interact in these overlapping locations? Some overdense regions will occur close to other overdense regions. How is the growth of structure affected when these regions interact? As normal matter accumulates in the centers of these overdense regions, it slows down, collides, and heats up. As that heat gets radiated away, how does that feedback affect the growth rate of these regions, including both the normal matter and the dark matter? And finally, when stars finally form in these very different environments to the ones we find today, how long do they live? How do they die? How does that impact the normal and dark matter that doesn't become stars? And what implications does that have for subsequent generations of stars and the growth of these early cosmic structures? It's important to understand that the answers to all of these questions are uncertain. They're firmly in the realm of the purely theoretical and are dependent on what details we include and exclude in our models and simulations. Are we using the correct models to identify halos, where a halo represents an individual overdensity in space? Or are we incorrectly treating interdependent halos as independent entities, or vice versa? Are we modeling the first stars correctly, including their initial mass functions and their death throes? Or are they heavier and more likely to directly collapse to black holes than we think? For that matter, do we even need stars to form black holes, or can these intersecting, inflowing streams of gas form the seeds of supermassive black holes directly, possibly with masses that are 10,000 plus times the mass of our sun right away? It's pretty clear that the first objects, stars, black holes, and star clusters, begin forming no later than about 150 million years after the Big Bang, and perhaps as early as only 50 to 100 million years after the Big Bang. But these ought to be relatively rare occurrences. How many big, bright, evolved galaxies we should see at slightly later times, like 200, 300, or 400 million years after the Big Bang, is a much murkier question. But we don't simply have our theoretical expectations, even with the appropriate uncertainties, to work off of. For the first time, owing to the unprecedented capabilities of the James Webb Space Telescope, JWST, we're beginning to discover and characterize galaxies found in these very, very early stages of our cosmic history. Prior to JWST, we had one confirmed galaxy, GNZ11, at an age of about 400 million years after the Big Bang, and only one other galaxy candidate, unconfirmed, possibly at an age of around 330 million years after the Big Bang. No other stellar or galactic signals from such early epochs had ever been seen. Fast forward to the present day. Less than 1 year after the JWST began science operations, and the story has changed dramatically. We have over 100 galaxy candidates from JWST that take us back to the first 400 million years of the universe, and several of them have already been confirmed to indeed be ultra-early and ultra-distant. GNZ11 already is now only the 5th most distant galaxy known, and it's fully expected that over the next 12 months, not only will the current cosmic record for distance, JADESGSZ130, from a time just 320 million years after the Big Bang, be broken, but that at least dozens of new ultra-early, ultra-distant galaxies will soon be confirmed. Many of these early galaxies that JWST is finding have peculiar, puzzling properties about them that appear difficult to reconcile with this theoretical picture that the universe has painted for us. They appear, for example, to be very massive, very bright, very rich in heavy elements, very actively forming new stars, and very rich in gas. The fact that we see so many galaxies with these properties so early on is puzzling, because we believe we understand how gas, i.e. atom-based matter, infalls onto these early galaxies, and how star formation feeds back and prevents future gas from falling in. There's a limit for how fast material can accrete onto these objects, and although certain physical conditions can lead to an object temporarily overcoming that limit, it shouldn't be sustainable over such long timescales. Therefore, when we look at these very early galaxies, we do get the impression that something is amiss. But what is it exactly that's amiss? A lot of people immediately resort to the spectacular or fantastical as far as explanations go. They assert that all of standard cosmology might be wrong, and perhaps we should throw out the Big Bang as the explanation for the origin of our universe as well. They hypothesize new laws of physics, like a new early form of dark energy that existed early on, or new physical phenomena, like the universe being born with supermassive black holes, or new exotic forms of matter, like a novel, long-lived particle that decays into normal matter at relatively late cosmic times. Bottom of form. But that shouldn't be your first resort as a scientist. That should be your last resort, after you've exhausted all of the mundane explanations. And there are a number of things that are quite mundane to consider. We should first make sure that these effects aren't playing a major role in causing these galaxies to appear with the properties they appear to have, and we should also make sure that our expectations for how the universe ought to behave are in line with the way the universe actually behaves. For one, the early surveys that are pointing to these conflicts are coming from very small and possibly atypical regions of the sky. There are surveys coming that will cover some 50 times the area that are showing these early galaxies, and we might well see a regression to the mean of this apparent effect. For another, it's possible that light from an active supermassive black hole at the centers of these galaxies is polluting our view and making us think that these galaxies are more massive and rich in stars than they actually are. A full spectroscopic analysis of these galaxies, not yet available, will be needed to determine if this is the case. For yet another, it's possible that these galaxies aren't actually brighter and more massive than we expect, at least not by the amount we've initially concluded, because JWST is overperforming. It could simply be the case, at least in part, that JWST's better than expected eyes make these galaxies appear brighter than they will turn out to be when properly calibrated. And finally, it's possible that we've gotten some detail like gas cooling, halo identification, the nonlinear growth of structure, or the effects of stellar feedback or magnetic fields incorrect. In other words, it's possible that either the preliminary data is unreliable, or that our assumptions for how the early stages of cosmic structure formation proceed are flawed. While there are some early observations that could wind up pointing to a tension between what JWST is seeing and what our current understanding of the laws and composition of the universe are, any such assertions that the Big Bang, or lambda CDM, lambda cold dark matter model, standard cosmology, is in trouble, are definitely premature at this point. Without better data, i.e. a deep, large area, robustly calibrated spectroscopic survey, we don't even know if these galaxies truly possess anomalous properties. An in-progress JWST survey, Cosmos Webb, should settle the issue. And even if they do, there are an enormous number of astrophysical possibilities that invoke no fundamentally new physics that could potentially account for why these galaxies would exist with these large masses and brightnesses. The only thing that would truly shock us at this point And to be clear, this is not what the data indicates at present, as if there's more mass inside these early galaxies than the normal matter known to be in the universe could potentially account for. It's entirely possible, even if these early galaxies are as bright and massive as the most optimistic estimates are, that boring old gravitation, electromagnetism, and stellar gas physics can explain what we see. A lot of people are making a lot of early, extraordinary claims about these galaxies, but we have to keep in mind that sound, responsible science progresses slowly and always follows the evidence. The important thing isn't to be the first one to speculate as to what the ultimately right answer is, but to get it right without unjustifiably crying wolf along the way. After all, no one can deny that the James Webb Space Telescope is giving us our best look yet at the early universe, and it may eventually help us to solve some of the biggest mysteries about our origins. As the JWST gathers more spectra and takes more images of distant galaxies, scientists will likely be able to start to resolve a true picture of what the universe was like billions of years before our Milky Way was born. And it's really worth waiting. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode. Subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.